All right, welcome to this lesson on lesson 1-8, summarizing quantitative data. We'll be talking about box plots and outliers. So the essential question we want to address today is how do we make box plots and how do we use them to compare distributions? How can we mathematically identify outliers? We want to be able to use the 1.5 IQR rule to identify outliers. We want to make and interpret box plots of quantitative data, as well as compare distributions of quantitative data with box plots. So what we need to know is what a box plot and a 5-number summary is in order to accomplish these learning goals. So to identify outliers, we use the interquartile range. You may recall that the interquartile range is calculated by taking your third quartile minus your first quartile. So let's write that over here. It's your third quartile minus your first quartile. And it could be used as a means to identify these outliers. So using the 1.5 IQR rule. So an outlier is an observation if it falls more than 1.5 times IQR above the third quartile or more than 1.5 IQR below the first quartile. So in other words, low outliers are less than the first quartile minus the 1.5 IQR. And the upper outliers, or the high outliers, are greater than the third quartile plus 1.5 IQR. All right, so this is the rule that we're going to be using to identify these. All right, so here are the data on the number of home runs that Barry Bonds hit in each of his 21 complete seasons. Identify any outliers in the distribution. Show your work. Okay, so the first thing we want to do, if we want to identify any outliers, right, then we're going to have to find interquartile range, which means we're going to have to find, the median and then work our way to the Q1 and Q3. So we're going to have to list these in order. So the first number is 16, 19, 24, 25. Okay, so I went ahead and listed out the rest of the numbers. So we sorted them in order. And then now what we want to do is figure out our median. So we're going to actually cross these out. So we got 1, 2, 1, 2, 1, 2. Work our way towards the middle. So we got one middle number, 34. So that's our second quartile, or our median, which means now we have two halves of the data. And we're going to find the median of each of those. So find the middle. So 1, 2, 1, 2. And here we have two middle numbers, which means we're going to average them up. So 25 plus 26 divided by 2, and that'll be our first quartile, which in this case is 25.5. And for the second half, we have these two middle numbers. So if we add them up, divide by 2, you're going to get 45. All right, so now that we got our quartiles, we can find the interquartile range. So it's 45 minus 25.5, which in this case is 19.5. Now for our outliers. So that means that our outliers, this is also known as our, so we can call it, so we can say our outliers have to be less than the first quartile minus 1.5 IQR, which in this case is 25.5 minus 1.5 times the IQR, or negative 3.75. So the outliers have to be less than negative 3.75, or the outliers has to be greater than that Q3 plus 1.5 IQR. So the outlier has to be less than negative 3.75 or greater than 74.25. So in this case, if we were to look at the 73, the maximum here is 73, right? And the minimum is 16. In this case, none of these numbers are big enough or small enough to be considered as outliers. In this case, this distribution has no outliers. So no outliers here. Again, it's important to actually calculate this and go through this process, go through the motions, because 73 would have probably been identified as an outlier had we not calculated this. So we want to actually make sure that when we're identifying outliers, that they truly are, mathematically speaking, outliers. Okay, so what are the importance of identifying outliers? Well, for one, they might be inaccurate data values, which is why we want to identify them correctly. So if we incorrectly identified 73 as an outlier in the previous problem, we may have inadvertently thought that it was an inaccurate value, which is not true in this case. In this case, it's perfectly fine by chance for him to have a value of 73 without being considered an outlier. But if you did identify an outlier, this could indicate that there might be an inaccurate data value, such as a measuring device error or recording error. And it can also indicate some kind of remarkable occurrence, just something that happened by chance. But also, the outlier is important to identify because it can influence the values of the other statistics, such as the mean and standard deviation. And we want to make sure that we identify it to make sure that we need to eliminate it if possible. All right, so if we want to make and interpret box plots, then we're going to actually need what we call the 5-number summary. So recall earlier, the dot plot, stem plot, or histograms were used to display distributions of a quantitative variable. Now we're going to be using another option known as the box plot or the box-and-whisker plot. So the box plot summarizes the 5-number summary. So what is the 5-number summary? It is a distribution of quantitative data that consists of 5 numbers: the minimum, the first quartile, the median, the third quartile, and the maximum, in that order. So box plot is a visual representation of this 5-number summary. How do we make a box plot? Well, we need to find the 5-number summary for the distribution. So we need to find those 5 numbers earlier. The minimum, first quartile, second quartile, third, maximum. Then we draw and label a number axis. We scale the axis with numbers, and then we draw a box that spans the first quartile to the third quartile. So in this case, you're going to find the 5-number summary. Which again we mentioned were those 5 numbers, which were the minimum, first quartile, second quartile, third, and maximum. Then you're going to draw a an axis just a horizontal axis, you're going to scale it with your numbers, and then you're going to draw a box that spans from the first quartile to the third quartile. So let's say that this was our first quartile, and this was our third quartile. Then the box is going to span from those two marks to make your box. Then we're going to mark a median with a vertical line segment. So let's say that the median was here. Then your vertical line segment goes there. Then you're going to identify the outliers using the 1.5 IQR rule. So let's say that this was an outlier. Draw the whiskers, lines that extend from the ends of the box to the smallest and largest data values that are not outliers. Mark any outliers with a special symbol, such as an asterisk or an X. So in this case, let's say we have the largest data value here. We'll call this the maximum, and we'll call this the minimum. So we extend the whiskers to the max and to the minimum without including the outlier. And then usually what we do is we draw a fence. We could draw a fence. This is a modified box plot where we draw a fence, and this fence is telling us our upper bound or upper fence. I'll call this an upper bound here. An upper bound for outliers. And we have a lower fence or a lower bound for outliers. And again, this was calculated using the Q1 minus 1.5 IQR rule. And this was calculated using Q3 plus 1.5 IQR rule. Alright, so that's how we do the box plot and how we modify it to include the bounds for the outliers. So let's look at an example. Ryan and Brent were curious about the amount of French fries they would get in a large order from their fast food restaurant Burger King. They went to several different Burger King locations over a series of days and ordered a total of 14 large fries. The weight of each order in grams is shown here. Make a box plot to display the data. According to the nutrition website, Burger King's large fries weigh 160 grams on average. Ryan and Brent suspect that their Burger King restaurants may be skimping on fries. Does the graph in part A support their suspicion? Explain. Alright, so first off, we want to make a box plot. So in order to do that, we need to sort the data, put it in order. Alright, so if we sort the data, we have 152, 159, 160. Alright, so we put it in order. Now let's work our way to find the median. Cross that out, 1, 2. 1, 2, 1, 2, 1, 2. So we got our median is between these two guys. So we're going to have to add them up. Divide by 2. So our second quartile is 166.5. Alright, so now we got the data. We got two halves of the data, including the 166 on the left side, and including the 167 on the right side. So now we work our way towards the middle on each side. So 1, 2, 1, 2, 1, 2. So we got ourselves our first quartile. 1, 2, 1, 2, 1, 2. So we got ourselves our third quartile. Next, we can find our interquartile range. So we got IQR equals 170 minus 163, third quartile minus first quartile, or 7. So we got our IQR of 7. We're going to need that, in order to do the outliers. So let's go ahead and do the outliers now, so that we actually already identified the outliers, or we actually calculate the IQR to identify the outliers, so we can calculate the outliers now. So let's do outliers real quick. All right, so the outliers have to be less than less than the first quartile, minus 1.5 IQR. Which in this case is 152.5. And then the outliers also have to be greater than 170 plus 1.5 times 7, or 180.5. So according to this, it seems that 152 grams is an outlier. All right, so we got an outlier. Now we can go ahead and start with the box plot. So we're going to draw and label. We're going to find the 5-number summary first. So the 5-number summary. So in this case, the minimum is equal to 152. The first quartile was 163. Second quartile is 166.5. Third quartile is 170. And the maximum is 173. All right, so we got step 1 here. Now step 2, we're going to draw a number line. And in this case, the number, we're going to label it. So in this case, this is the weight of the large fries. In grams. So for our scale, we'll start with 150, since that is actually below the minimum, and we'll end at 175, and then we'll go by 5s. All right, so now we can go ahead and start labeling. Drawing our box plot. So the minimum of 152 is around here. So I'll mark that. First quartile is around halfway between these two. Second quartile, around here. Third quartile, and maximum. Now keep in mind that we said our minimum is actually an outlier, right? So this right here should be labeled with an asterisk or some kind of X to identify it. So this one we said is an outlier. So therefore we're going to look to our second highest maximum here, which is 171. So we're going to mark 171 as our new, quote unquote, new maximum. All right? So 171, or I'm sorry, not 171. We're not looking for a new maximum. We're looking, I apologize for that. This is our outlier, not 173. That was our outlier. So we need a new minimum. In this case, the new minimum is 159. So this is our quote-unquote new minimum. I was looking at the wrong end. So 159 is around here, and we'll mark that there. So we got our box, and we got our whiskers. All right, and then we'll label our upper fence and our upper boundary and lower boundary. So this is like our lower boundary. This is our upper boundary. So 152.5. is here, and 180.5 is around here. All right, so then to answer the second question, according to the nutrition website, okay, so does the graph from part A support their suspicion about the fact that, about the claim that Burger King's large fries weigh 160 grams on average? Well, no. From the box plot, the first quartile is actually 163 grams or more. So if we look, so if we label from part B, so if you look at first quartile over here, this is about 163 grams. Okay, so the first quartile is 163 grams, which means that at least 75% of the large fries weighed 163 grams or more. Why is that? Well, because this is 25%, this is 25%, and this is 25%. From here to here is 25%, from here to here is 25, from here to here, and then from here to here. So at least 75% were actually greater than 163 grams. So this means that only the outlier and the one other order, which is 159 grams, weighed less than 160 grams. So 75% of orders were larger than 163 grams. So in this case, we would say there's not enough evidence. So there just isn't enough evidence to show that they might be skimping on the amount of fries in the large orders. So this is another useful application of the box plot. It gives you the percentages of data, which means that this kind of helps you determine if you can kind of support a conclusion or not. But we'll be talking more about this in future chapters, how to actually go about doing an experimental test for this. All right, so if you want to compare distributions with box plots, you want to look at a couple of things for the shape. You want to look at the whiskers and the median in the box plot to determine the shape of the distribution. So if the whiskers are about the same length and the median is around the middle of the box, we call the distribution symmetric. If the right whisker is longer and or the median is to the left of the center of the box, the distribution is skewed right. So notice that when the median is to the left of the center of the box, it's actually skewed right. So it's kind of like the opposite. It kind of has opposite what you kind of think. And if the left whisker is longer, and if the median is to the right of the center, then it's skewed left. So if you look at this, the graphs below, well, the median is in the middle, the whiskers are about the same length, so this right here is symmetric, or at least roughly so. Now for the middle graph, notice that the center of the box is is here. So this is the center of the box, and it is to the median is to the right of the center, which means that it would be skewed to the left, and also the left whisker is longer as well. So this is skewed left. And then for the right one, the right whisker is longer, and if you look at the center of the box is here, and the median is to the left of the center, so it's skewed right. So most of the time you'll be able to identify the shape using these guidelines. Alright, so for their final project, a group of statistics students wanted to compare the texting habits of males and females. They asked a random sample of students from their school to record the number of text messages sent and received over a 2-day period. Here are their data. Parallel box plots of the data and numerical summaries are shown here as well. Compare the texting distributions for males and females. Alright, so we got the data, and we want to just compare the actual distributions here. Well, first off, if you look at the shape of the distributions, let's do that first. So in this case, the middle of the box is here, and this is to the left of the middle. In the middle of the box for the other guy, and this is kind of close to the middle of the box. So I would not use this guideline to determine whether it's skewed left or skewed right. I would look at the whiskers. So we won't be able to use a guideline here because it's too close to, to kind of tell. But we do know that the right whisker is longer, so this is also skewed right. So both distributions are skewed to the right. All right, so now let's go ahead and compare. Also, keep in mind that since both distributions are skewed to the right, this means that we want to use, we need to use the median and the interquartile range to actually compare the center and variability. So to compare center and variability. Okay, so now we got the shape and we know which measures of center to use. So this means that we are actually going to be determining the center. So if you look at this, the females typically texted much more over a 2-day period, since the median was 107. So in this case, females texted more on average, since the median for them, the second quartile, so if you look at the second quartile, that's this guy here, is around 107. Than the males did. Now, second quartile for males is all the way down here, which happens to be around 28. So if this is like the 50 mark, so around 28 or so. So around 28 text messages. Now also keep in mind that the median of the females is above the third quartile for the males. So if you look at this median here, it's actually above this third quartile for the males. So this means that that the females texted more than 75% of the males, because this right here represents 75%. So if you think about it, the females actually texted more than 75% of males, which is quite interesting in this study. Now let's talk about variability. So there's definitely a lot of variation in the female distribution compared to the males. So if you look at this, the female distribution is quite spread out from left to right. And if you compare the IQRs, so if we were to actually calculate the IQRs, so notice that this right here represents the IQR for the females. It's definitely larger than the IQR for the males. So the IQR for females is larger than IQR for males. All right, and now let's consider any outliers to compare the distributions. So there are 2 outliers in the male distribution, whereas the female distribution has no outliers. So 2 outliers in the male distribution. Whereas there is no outliers in the females. All right, so we compare the 2 distributions. Seems like on average the females text more over this 2-day period, according to the sample that was taken. At least 75% of most females text more than about 75% of males, and there's definitely a variation in the female distribution. So some females are really on the low side, and some females are really on the high side. All right, and that's it for the lesson, guys. So in the next lesson, we'll talk about describing location in a distribution.